Okay, so let's get started. So welcome everyone. So today, I already sent you an abstract of what I'll be talking. So I already said the main takeaway from this talk would be that you get the general idea of what machine learning is. And so I'll just get started without much further ado. So first I'll start with some motivation, like how machine learning can actually help in solving problems. So start with motivation. I hope my board is clear. So I'll be confined to writing in this region, I think. Yeah. So yeah, let's start. Motivation for so there are many ways to motivate. Like there are thousands of problems where you can actually motivate the need for machine learning. But since currently I'm doing my internship in a healthcare domain, so I thought maybe I'll try to motivate machine learning in that sense. So I'll try to motivate from yeah. So how exactly this machine learning can help in this healthcare domain? So let's take a very simple example. So let's say there is a patient. So I'll just not write much. I'll try to explain via diagrams. So let's say I have a patient. Oh yeah, and before that, so what I plan to do is, so I think we have almost like 2 hours of lecture. So first I will lecture for like about 45 minutes, and then we'll have a break come QA session, where in the QA session you can ask me like anything that I've like explained till now, and so I'll try to answer those in the break session, and then we'll have again 45 minutes of lecture. After which there will be another QA session where you can ask anything. Okay. So let's explain by a diagram. So let's say there is a patient. Just mind my artistic capabilities. Let's say there is a patient, and he's sort of suspicious that he might be having a particular disease. So you can take this disease to be anything, like your favorite disease, like whatever you like to have. So let's say we take something, say pneumonia, sepsis, or anything. Let's say we won't be much bothered about what the disease is. The main focus is just to explain the idea. So let's say I take the disease to be, let's say, pneumonia. Let's say the disease we're looking for is pneumonia. So he goes to a hospital. So he goes to a hospital. So this is the hospital, and there are staffs, like there are medical staffs, and they assign him to a doctor. So, and then the doctor. Now the doctor examines the patient, and he has to sort of come into a conclusion, like whether this patient does have a disease or not. So what the doctor does, let's say he measures, let's say 4 parameters. Like these parameters can be anything. Like abstractly speaking, these parameters can be any vital signs like heart rate, blood pressure, or any lab parameters like SCO, like any chemical that's there in lab. So we won't be much bothered about what the chemicals or vital signs are. So let's say the doctor measures lot of parameters. So let's say he measures So now these parameters can be anything. Like, so for concreteness, you can take, like for your example, you can take x1 to be heart rate or x2 to be, like as I said, blood pressure. So we won't be bothered like what these actual parameters are, but rather we will look at abstractly. Okay. So since I'm running out of pace, I'll have to route this, I suppose. Okay. So I hope till now the setting, what I'm trying to describe to you is pretty clear. So if you have any further question, just write it. I'll try to answer them in the Q&A session. Okay. So let's say the disease that we're looking at, it's sort of Y. So here your Y is sort of pneumonia, is a sort of variable which is sort of representing pneumonia. So let's say, so after doctor examines all those parameters, there are two outcomes. Either the patient is positive of the pneumonia or not. So let's say I define this variable to be 1 if patient is positive, or 0 if the outcome is negative. Yes. So now, so this is the Y level, I can say. So now, so this Y level in our model depends on 4 things: x1, x2, x3, and x4. So the way I can write it, it's like this. So let's say, so this Y level is but a function. So many of you might not be knowing what a function is. So function, you can right now think of it like it's like a machine. You give an input and some output comes out. But there is one restriction, like for one input there can be exactly one output. So you can't have like a multiple output thing. So the Y level is sort of a function of say x1, x2, x3 and x4. So this Y level is a function of x1, x2, x3 and x4. Now, like right now we're not bothered like what these parameters are. We're just looking at abstractly. So if I can find a function f based on this parameter, like which sort of outputs the label either 1 or 0. So that's very efficient. Like if we can find such function, that will be very helpful for the doctor. But in most cases, you actually cannot find the underlying function. So what is the so the machine learning tries to answer the question like what best we can do in that sense. So maybe we cannot exactly compute the function, but maybe we can have some estimate. So that is the underlying philosophy of one part of the machine learning, which is called predictive modeling. We are trying to predict this function f based on our data. Okay. So yeah, so this is the type of problem like which is called classification, and also like in a more general sense is called supervised learning. Okay. So we'll look at this example more in the logistic regression part. Okay. So now I'll move on to something, the general idea or the general framework of how machine learning models are built. Okay. So I'm rubbing it. So now like in this in the current economic situation or in any market that we talk about, there are tons of data, right? Like data are coming each and every day, tons of data are being produced every day, and you just cannot look at those huge data sets and conclude some pattern out of it. So we need better tools, better representation to understand and extract information out of them. So that is also part of data science, where you do a lot of exploratory data analysis and visualize your data so that you can extract more information out of it. Okay, so now we'll go to general. Machine learning. So I'll try to explain each like this idea, like in a via diagrams. So first we have a data. So these data are huge data. So let's say we might have data of patients in a healthcare domain, or the data of like a stock price, or like the data of like real estate properties and all. So we can have a huge data, right? Like this data can be huge. So machine learning can only be applied and make sense when you have a huge data set. And that is also the philosophy of statistics, right? Statistics looks at like large data set and try to extract sort of information out of them. So yeah, we have a data. So it's large, or rather it's a big data. So now we have a data. First, you split your data in two parts. One is for testing, another is for training. So first you have to train. I'll explain each of like what does this mean, training and testing. So you split your data. So let's say you split in two parts. So one is training. So you use one part of your data for training, like to build your model, and the other part is for testing. See, right now I'm not giving you any general definition of machine learning. Like I think at this level it doesn't just make sense to give you just the definition of machine learning. So I'm just trying to motivate. I'll give the definition later, but I'm just trying to motivate the definition by an example. I think this is like one of the efficient way of learning. Yes. So we have train and test. So you train your data and build a model, and like so let's say so in our previous example of the healthcare domain, so what we mean was, so there was something like this, like y level is equal to f of x1, x2, x3 and x4. So building the model means you're sort of trying to estimate this function. So here you build your model. So with this trained data, you build your model. Right. So that means you have an estimation of this function f. And then after you build the model, you test your data. So you have a test data. So you plug in this test data into your model and see how accurately it is predicting. So after this, you check. After this, you check for the accuracy of your model. Like let's say accuracy by means like it's on the test data. Let's say it's predicting with like in 90% of the cases is predicting the actual true level. So the accuracy of your model will be 90%, like that. So you check your accuracy. So let's say your company or any organization that you're working, like sort of demands that you should have at least a model of 80% accuracy. So if you, after checking the accuracy, if you see your accuracy is 85%, you say, okay, I'm happy with my model, so I'll sort of now put this model in the market. And if you're not satisfied, then what you do? So if you're not satisfied, you gather more data. And again follow this procedure. Y data, you train, test, and then you build the model. Now, so one question that might pop into your head, like, so let's say you have, data is on 10,000 patient. Like, how exactly would you like to split your data? So yeah, that is also a very interesting question, and there is no thumb rule actually that you can do to that you can apply to sort of split your data. So usually we like to keep in the ratio of 7:3. So let's say you for training you take 7,000 patient data, and for training you take 7,000 patient data, and for testing you take 3,000. So yeah, in the internet you will find a lot of articles over like how you can split your data efficiently. There are a lot of like papers and also sort of maximization algorithm as well that you can look at. Yeah. So this is the overall structure of machine learning. So under every machine learning thing, this is what actually goes on. So whatever technique that I'll be describing to you will be based on this philosophy. Okay, so I think so we have a general understanding of what machine learning is. At least you have some heuristic understanding of what is. So that's why it's named at like heuristical introduction. Like I generally prefer like describing all these things like in a mathematical way. But since it's really beyond the scope to actually describe all these things mathematically, because it will use a huge amount of probability theory, and that is really advanced, and a lot of statistical tools, multivariate calculus, and linear algebra, and also like advanced coding as well, I think. Okay. So now I'll describe some of this machine learning technique. So let's say first I'll start with let's say regression. So just to motivate this idea of regression, I'll try to use a bit of mathematics, of course, a bit of mathematics. So let's say we like in the xy plane. So let's say in the xy plane we have a lot of points. There's something like this. Like this, like you have some scattering of points over the plane. Now I'm pretty sure they don't at all look like that they lie in a straight line, right? They don't at all look like they lie on a straight line. But an interesting question to ask. Maybe I just so since we are only in this part of the plane, so I'll just cut short this axis. So okay, so question of interest is, can you some way like sort of, so there are a lot of mini lines that you can draw, right? So you can have this line, this line, this line, and somewhere or the other we want to find the best line, so what is the meaning of this best line? So what is the meaning of this sort of best line? So we are trying to find a line which will sort of best describe the data in a linear way. So I'll explain like what this best actually means. So here I'll use a bit of geometry as well. You will see. Let's draw out this line. So since I think we're almost in 9th standard, like I don't know, maybe you know what equation of line means, right? So the equation of line will look like this. Right? So y is equal to some coefficient plus beta 1x. So let's say I have this line. So this is the equation of the line, y equal to beta plus beta 1x. And we look at this. So from each point we draw a line parallel to y axis. So when you talk of distance of a point from a line, so we usually mean like this perpendicular distance, right? This perpendicular distance. We usually mean this perpendicular distance, but I'm claiming that it's almost equivalent. Like if you are sort of trying to find the best line, it's almost equivalent to look at this line segment rather than this line segment. So here and to prove that, I'll use some geometry things. So let's say we just look at this point. This is the perpendicular thing. Let's say I draw this. Okay. So this is also 90 degree, and let's say this is the angle theta, and let's say this is his distance d. Right. So let's say this is A, this is B, this is C, this is D. So many of you who might be preparing for RMO and all like are able to just predict this A, B, C, D is a cyclic quadrilateral, right? So this is 90 degree, this is 90 degree. So they sort of lie on a circle. So this angle is equal to this angle. I want the properties of cyclic quadrilateral, right? So if this distance is D, then what will be this distance? It will be d cos theta. Okay. So similarly, if you have this distance as well, so then this will be this distance times the cos theta and all. So it's almost equivalent. So it just is. So this distance and this distance just differ by a factor of cos theta. So they are almost equivalent in some sense, to look at either this distance or this distance. So okay. So now I try to describe what this best means. Okay. So I'm just rubbing this whatever geometry I did. Okay. Oh no, fine, I'll just keep it. So let's say the points that I have in the plane are, let's say I now label them. Say now x1, y1, and let's say x2, y2, and so on. So let's say there are endpoints. So there are endpoints. So those endpoints I sort of label, let's say x1, y1, x2, y2, and going up to So xn yn. Okay. So these are my points. I haven't labeled all the points. It's not, it's not worthy to waste my time on just labeling these points. So let's say I label all those segments as well. Let's say this is D1, D2, and so on. So I calculate all these distances and I square them and then I sum them. So let's say I take all these distances, D1, D2, D3, and so on up to Dn, and then I sort of square them. Like you actually may not square them, but I'm just squaring to make my life simple. To make my life simple a bit, you'll see later why. The D1 square, D2 square, D3 square, like Dn square, so on. Now you add them. So now you got a real number, right? So we have this expression D1 square plus D2 square plus D3 square and going up to like Dn square. Like so the best. So when I say the best line, so what it means was I want to find a line which sort of minimizes this sum of square. Okay. So I think now it's clear what this best means. So I'm trying to find a line, like, so there may be a lot of lines, right? So I'm just trying to find one line that will minimize this expression. Okay. So now I'll tell you how. And okay. So now let's say I'll also rub this, and just since this is very messy diagram, I'll just take fewer points to explain it in a better way. So let's say I have this one. Let's just take 3 points. Or with a line. Okay. So let's say this was my okay. So this was my say x1 and y1. Right, and this is the expression of the line is not beta y. Okay. So now if I draw a line parallel to y-axis, what do you think this level is? So the level is x1 and beta naught plus beta 1 x1, right? Because this point lies in this straight line. So now what is this distance? d1. So I'm pretty sure you must have done this. The d1 is inverse root of this x1 minus x1 square, like which is sort of pretty obvious to be 0, and so it will be nothing but, like if you just do it, is mod of y1 minus beta naught minus beta 1 x1. Right. Now you square them. So I told you like why. Now I'll say why I need to square, because if you have learned calculus, you will see that the function y equal to mod x is not differentiable, and for our analysis this differentiability is kind of necessary. So I'll just square them. So if you square them, and this like this, right? So similarly I'll have dn like this, yn minus beta naught minus beta 1 xn whole square. Now, okay, so now let's say I look at this expression, some function, okay, use another notation. So let's say f of something of the summation of di square. So this is just a shorthand notation for the expression that we had earlier, the sum of all those d squares. So, so this expression equivalent to yn. Beta naught is beta 1 psi square. Okay, so this is the expression. So you see all my yi's and xy, they are known points in the plane. Okay, so the only unknown that I have is beta naught and beta 1. So you'll also be seeing that if I vary my beta naught and beta 1, this line will change, right? And we are sort of trying to find the best line, or in other way put it, best beta naught and beta 1 such that this expression is minimized. So this expression is sort of a function of beta naught and beta 1. So here I have beta naught and I have beta 1. Okay, so now my aim will be to find, okay, so I'll just write it. I hope you can see this. Our aim for now is find this pair and beta 1 such that this f of naught beta 1 is minimized. So now you see I have two unknowns, beta naught and beta 1. So if I had only one unknown, like you can apply your class 11 and 12 knowledge to sort of minimize them. You differentiate and then you again differentiate and then you put the first differentiation to 0 and figure out the value of beta naught, and then you put in to second derivative and check for minima or maxima, right? But now we have two unknowns, so how do you go about it? So here comes multivariate calculus, and so right now I don't think I'll be spending time on it because I have lots of other things to discuss. But I'll so it will be a very good exercise for you to like go over to the internet and find out how this beta naught and beta 1 are sort of calculated. And one of the interesting things that you will find that this line goes through the sample means. So for some of you, like all these means samples may not make sense, but you just go over to the internet and try to figure out what this beta naught and beta 1 is. And the value of beta naught and beta 1 that you will be getting is sort of related statistically to not statistically, like it's related to the statistical moments of this values x1 y1 and x2 y2 and so on up to x and yn. Okay, so like if I spend a lot of time on the mathematics, like I think this whole 2 hours will, like maybe it will take more half, like 1 hour to sort of find the beta naught and beta 1. So I just won't dive into those things. Okay. So some of you like who has like calculus background can go back and actually check how these beta 1 and beta 1, beta naught and beta 1 are calculated. Okay. So, okay. Right. So now we have sort of found like the best line that sort of represent this scattering of points in a best linear way, right? So now, okay, we have found out like, but what to do with it, right? So now these are the tools that I've kind of now described to you. Now I'll try to give a practical example to sort of explain like how this this whatever thing, like a little bit of math that we did is kind of helpful and applied. Okay. Okay. So now, so there are various type of regression. Like there are actually, I know something like 7 to 8 regression, linear, multiple, like Bayesian, random forest, decision tree regression. But all those are very advanced topic at this level, so I won't dive at all. So I'll just stick with basic things, something called simple regression. This is something called simple linear regression. So let's say, so a place where this regression thing is applied is in weather forecasting. So we'll look at a very simple application to weather forecasting. So let's say you want to predict tomorrow's weather, like based on only one parameter. So this is actually insane to just claim like this your weather is dependent only on one parameters like precipitation or pressure, whatever. But just to describe you, I'll just assume like this weather thing. Weather I mean just the temperature. Let's say that's it. I'm just interested in the temperature. Let's say temperature sort of. So this is called sort of related only to like sort of not related. So in machine learning term it's called regressing. So if I'm regressing temperature on let's say I do it on let's say rainfall, precipitation. So this variable I denote it as T and this variable I let's say denote it as T. Right. So in machine learning language, I am regressing temperature with precipitation. All right. Okay, fine. So, like so as I have described to you, so I am sort of trying to predict the weather for tomorrow. So what is the idea? So for that you need sort of okay. So let's say I have the data of last 1 year, or yeah. So let's say I have data for last 100 days of temperature and pressure. So let's say I have T1. So T1 is the and T1. So T1 is the temperature of yesterday and P1 is the temperature of yesterday. And similarly you can understand what this P2 means. It's the temperature of day before yesterday and this is P2 is the pressure of day before yesterday, and you can understand what I'm trying to actually go at. Okay. So, and P100 and P100. Now I have all these data of T1, P1, T2, P2 and up to T100 and P100, right? So now I am interested to predict today's temperature. So how will I do that? And how will I apply the a bit of mathematics that we did like just before coming to this application? So I'm just rubbing it. I have shortage of space. So I have this data P1 and P100. So So let's say I plot them in a graph, in an XY plane. So I plot, let's say this is my P1, P1, this is my P2, P2, and so on. This is my P100 and P100, right? So now I have this data. Now what I do, I try to find the best line that we have that I told you earlier, right? So we find the best line. And so if I find a line where, let's say this P equal to beta1 plus beta1 T, right? So now I have a best line, which is P is equal to naught plus beta1 of T. Okay. Now I have, via this best line, I have figured out the best linear relationship that it can have. So let's say I know. Oh, sorry. Yeah. Right. So okay. Fine. Okay. So maybe we'll change one thing. Oh no, whatever. I think the idea remains same. So let's say zero transforming. So I have found my beta1 and beta naught and beta1. This is P over like 1 by beta1 minus beta naught by beta1, right? Because I have transformed it like this. I hope I'm right. Yes. Yeah. This is. Yeah, I think I'm fine. Okay, so now let's say I know today's pressure. So let's say if I know today's pressure, which is P star. P star is today's pressure. There's pressure. Then if I plug in this value of P star in this equation, then I get a value T star. Is the prediction of today's temperature. So now this temperature. Okay. So now, like if you're in a weather forecasting company, then you can actually tell, okay, so I have, after building my model, so this is what I got as my estimated temperature. So you have now a prediction of today's temperature, and how you arrived at this prediction via all those best thing that we did. Right? So this is a very, very simple application of like what is called simple linear regression and predictive modeling. So I think for regression, okay, I'll describe another thing, just a higher version of it. So now, like if you don't get whatever I'm going to say next, is fine. I'll just say it for 5 minutes, and then maybe we'll have our break. So let's say, so it's not good, right? Sorry, I think I'm going out of the camera. Okay. So let's say it's not at all good, right, to regress your temperature only on this precipitation. You like to have it on a lot of other parameters as well. So you like to regress your temperature T on a lot of other factors, X1, which may be precipitation, maybe pressure, maybe some radiation and all, whatever. So you might have to regress it on, let's say, m variables, x1, x2, and xm. So like how do you sort of regress it? So what you have to do is, then you will have to plot, let's say if you have a lot of data points like this. So you like to plot all those data points in m+1 dimension, but as you know, you can't go beyond like dimension 3. So this is where linear algebra and multivariate variable calculus comes into play. Alright. So I'll just describe how you do it. Not how you do it, but just how to model it. So I have t as side, let's say they are the constant factor beta naught. Okay, and one sum plus nxn. So what you do, you regress. So you sort of want to have the best linear representation. Again, best linear representation of this kind. So you'd like to have the best estimate for beta naught, beta 1, beta 2, and going up to beta n. And for that, you will need a lot of advanced tools that is actually beyond the scope. And we also require a lot of very advanced linear algebra to tackle this question. So after you have estimated them, you can have a sort of a prediction, right? Okay. So so this is what we call multiple linear regression, because you have multiple variable, not a simple one where you have only one. Okay. And now I'll describe another thing, which is just a very special part of what this multiple thing is. So this is called multiple linear regression, because you have multiple parameters and it is sort of a linear relationship. Okay. So now I will discuss something called polynomial regression. So this is just a special part of this thing. So rather than taking it to be a multiple parameter, what you do is you take a single parameter only, beta 1 x, and look at the higher powers. So this is, you can say, polynomial regression in one variable, I can call it, because there is only one variable, x, x square, and so on. You can also have multiple variables, like let's say a1y plus a2y squared, and so on. So n, what is what n, and also, so why only this power? We might also like to have a lot of like cross terms as well. So cross term is something, what about like this c1 x times y, or c2 times some x cube y and something like that, like powers of x's and y's combined together, and so on. So you see, I'm putting more and more layer to my regression. So this is how you can sort of generalize from simple to a very high dimensional thing, and the more higher you go, the more advanced thing you need, I think. So I think this is it for the regression, I think. So now I think if you have any question, you can ask it on the comment, and I'll try to answer them. So now we'll have a Q&A session for, let's say, 15 minutes. Then we will talk of another topic called classification. Okay. So if you have any question, please ask. So this is sort of break, and okay. So you have 5. So just ask your question in 5 minutes. I'll try to answer as many of them as possible. Break. And just see if there are any questions.
There are no questions.
No. So you can ask me question later also if you cannot figure it right now, I think. So now we'll have a 5-minute break. You can ask question like in between, and then we'll start, I think, our next session from I think after 5 minutes I'll have a Q&A session if there are any question. Like, otherwise I'll just move forward with my next topic. It is actually a very nice question. So I'll just try to answer them, like answer that. Probably stop there. So the question that was asked, I think, like, while doing regression, like, why is it a line, or we can have a polynomial as well, and to a different structure of the data. So I think like what you tried to meant was something like this. So let's say if we have a data like which was like this, let's say. Like this, or maybe not like this. Let's say something like this. So I think I'll just make more explain it better. Okay. Let's say you have something like this. So let's say you have data point like this, right? So if you try to have a linear fit like this, it's not actually a very good approximation. So maybe it's looking more like sort of a parabola and 2-degree equation. I think something like this will fit better, right? If I have something of this kind, I think this will fit better. So in this case we'll go for polynomial regression. So there are a lot of method of regression. Like I think sort of tried to describe in detail the simple linear regression. Then I also told you about multiple regression and polynomial regression. So like which regression that you are going to apply, that's up to you. That's up to you. Okay. Right. So here I think you will go for a polynomial regression. Okay. So I think I'll wait for more 2 minutes. If you have any other question or have question related to that, then I'll go for the next one. Okay. Any other questions? So okay, so we'll move forward to the next topic, which is called classification. So if you have any further question or regression, please do ask. I'll be more than happy to answer. And I hope like the question that some of you have asked have been answered. And like if you have more doubt on it, please ask it on the next Q&A session. So now we'll look at something called classification. Okay, so before that, in machine learning there are 3 types of settings or 3 types of sort of learning. I'll just try to describe to you that the machine learning is divided into 3 parts mostly. So, ML. So we have something called supervised learning. Okay. And then you have something called unsupervised learning. And another thing is called reinforcement learning. So whatever I have been describing to you is a part of supervised learning, and we'll be mostly focusing on that only. So maybe if I think this I cannot tell you what these things are actually. So you have this. Terms. You can just Google it and find out what it means actually. I cannot sort of describe to you right now, like what this reinforcement and unsupervised is. But mostly what I've been talking about is called supervised learning. So this regression, so under supervised learning, regression is one of the part. Regression is one of the part, and another part is called classification. Classification. So now I have sort of tried to give you a brief idea of like what regression is. Now I'll try to describe what classification means. Okay. So So classification. So I think the problem that we'll be interested in. So I think I've already told you the motivation that I gave to you. So that was some sort of a classification problem, because I don't know if you remember or not. We have this y level sort of function of, let's say, one, right? We had this earlier, remember? So this y level was our sort of leveling of whether the patient is positive or negative. So you have 1 if the patient is positive, and it's 0 if it's negative, and and now we want to estimate this function f, right? x1, x2, x3, and x4. I'll give you a sort of rough solution of what you can actually do, like in this case, to get this sort of function. So for that I have to go layer by layer, which is not that easy, and it will actually take some time. So maybe you will because I want to at least describe to you this regression and classification thing, because it's very basic, and the idea, you must have these ideas to get started in machine learning. Okay. So maybe I'll spend some time on it. Okay. So be prepared for a bit of mathematics. Okay. So for doing classification, so there's a very important mathematical curve that we sort of use. There are a lot of other curves that you can use, but like mathematicians, data scientists have realized this is actually a very nice function to look at. So the function that I'll be describing to you right now is called logistic curve, or something called logistic curve. It's also called sigmoid curve, because the you'll see why it's called sigmoid, because of the way it looks. So the form of the function is like this: f of x equal to e to the power x by 1 plus e to the power x, and the domain of the function is real numbers. So x belonging to real numbers. Okay. So the domain is real numbers. So I'm pretty sure, like some of you might have already figured out like what is the range as well, right? So the range is, so this range of the function between, so range of the function f, and the value that the function take is between 0 and 1. This range of f contained in 0 and 1. So it's so that I think the exact range will be sort of, it never takes the value 1 or neither it takes the value 0. So the range of the function is exactly 0 to 1, like the open interval. Now I'll plot the function. Okay, so if you plot it, like there are a lot of techniques to plot. I'm not going to describe all those techniques how you can plot functions. I just simply plot it, or you can just plot this function using softwares like MATLAB or R. Whatever. So an important curve to look at is a sigmoid curve. Okay, for the classification problem. So and the curve look like this. So you can see like so this function is called the logistic or sigmoid curve because the shape of the curve is like an S, and the values of the function lies between 0 and 1, and also these two lines are usually called the sort of asymptotes, because the curve is sort of approaching those lines but not exactly touching it, and as the value of the function lies between sort of 0 and 1, so what you can sort of understand is that since the values of probabilities are also between 0 and 1, so this function will sort of help us in modeling the probabilities. Okay, and this we'll use to actually solve our the hospital classification problem that we have. All right. So our aim right now is to estimate the function f, where in the hospital level problem we had this y level sort of like a function of now we want to estimate this function, which sort of outputs you either 1 or 0. We will see how the logistic function actually help us in finding out this f. So let's say I denote p as the probability. Okay. So let's say I denote p as probability that so let's say my P is the probability that the patient is indeed positive. And first, rather than trying to find exact level, we sort of model this probability and try to find, like, can we have an estimate of this probability, and for that we'll sort of intertwine whatever regression we have learned as well. All right, you'll see we'll use multiple regression to multiple linear regression to do this. So, but it's not exactly linear regression because the way the coefficient will be found is actually a bit different. So yeah, you'll see. So rather than looking at P, how we do it? We look at log of P. P was the probability of the patient having the disease. Is sort of in a linear way is sort of like this. Let's say beta 1 to beta 0 plus beta 1x. And so if you solve this, you will find that this P is nothing but the probability P is nothing but e to the power beta naught plus beta 1 is 1 plus beta 2 is 3 plus beta 4 x 1. It's not a very huge equation. No. This is the 1 plus or again beta 1 naught beta 1 x1 beta 2 x2 beta 3 x3 plus beta 4 x4. Okay. So you see, this is a very huge long expression. But this is, so if I denote all this variable like as a simple complete y, let's say this is e to the power y plus 1 plus e to the power y. So it is actually a sum from the sigma curve that we have sort of learned. Alright. So you can estimate this beta naught, beta 1, beta 2, beta 3, beta 4, but not in the way we have learned, I think, but like in a linear way. So the way to do it actually comes from a very heuristic approach, which is called maximum likelihood and all. So the mathematics behind it I can't describe to you over here. So for that you will have to look at the reference that I have sent you. I think in my abstract I have sent you a reference on Introduction to Statistical Learning by Gareth James. So there you will find all the mathematics behind it. But I think right now you can just skip those because that's a bit advanced thing. So maybe in future, if you come across such things, you can have a look at the mathematics. But right now you should try to like get whatever the ideas I'm trying to sell to you. Okay, fine. So now let's say a patient comes to a hospital and the doctor sort of have already measured these values x1, x2, x3 and x4. So okay, so let's have now run this, not this. your probability is a function of x1, x2, x3 and x4. So once the doctor have measured x1, x2, x3 and x4, you can actually compute the probability. Now from this probability we'll go for the function f. So how will we define this function now? Like this. So we'll say like this is equal to 1 if p of x1, x2, x3, x4 is greater than 0.05, okay, and 0 if p of x1, x2, x3, x4 less than equal to 0.5. So you might ask, why did I choose 0.5? Since I don't have any prior information, I'll just do symmetric boundary like 0.05 and 0.05. So in a curve, a logistic curve that we have drawn earlier, so we had this, right? So this is my 0.5. So after computing the probabilities, if I see my value lies above this curve, so this will be a region of positive case, and if not, then if the value of the probability is this below this line, then that will be a negative. So that will be a case for the negative patient. This is the negative. Alright. So in some way we have found a function. So look how we have got the function f. So first we did some form of regression to find out p, and after we have computed p, we found this function f by drawing some cutoff boundary. So now we have in some sense sort of solved the problem, because we have given the doctor this function and all the values of those parameters, and based on that you can predict in some way like whether the patient is positive or negative. Alright. So now you might want to check how much accuracy this model gives you. So for that you have to go via the general machine learning thing that I've talked initially, the general structure of the machine learning thing. You divide your data into train and test, and then if you're satisfied with the accuracy, you go for the model. Otherwise you collect more data and go for it again. Alright? Yes. So this is sort of an example of classification, and so I think for the classification part I'll just say up to this only. Now I'll try to describe to you a lot of various other ideas, like I'll describe more two things: decision trees and k nearest neighbors. Okay. So I won't be diving at all much deep into decision trees. I'll just give you a brief idea of what decision tree is. So you see, previously people call it classification because it's sort of classifying, right? like whether the patient is positive or negative. So rather than having, so this is called binary classification because we have two output, 1 and 0. So you can also have multiple classifiers, like where you can have like sort of 4 or 6 output and things like that. But I won't be telling you this, but you can actually Google all these things and find a lot of relevant articles and materials on it. Now decision tree. To give you a very easy sort of, and okay, I think I have to. Yeah, now it's fine. Yeah. So let's say you want to, based on something, you want to predict whether a person is fit or not. Okay. So let's say you have a person's age. Let's say. So decision tree is like you sort of have structure like this. It's like a tree. Okay. So we want to see how this tree can actually help you understanding various things. So we have this age. So let's say so now we want to answer the question like whether the person is fit or not. So let's say I say if the person's age is, let's say greater than 40, then sort of it goes over here. Otherwise, if it's sort of less than 40, so we subset our entire population into two classes, where in one class we have all the people whose age is greater than 40, and another class where we have all the people whose age is less than or equal to 40. All right. So now we answer another two questions: whether that person eat a lot of junk food or not. And another thing that we'd like to have is whether the person does exercise regularly or not. This is one thing, and this is another. So if yes, then the person is not fit at all. Like if the person doesn't eat a lot of junk food, then you might say yes, indeed the person is fit. And if he does a lot of daily exercise, then yes, goes. If no, okay, so something like yes, then yes, the person is fit, and if no, then no. Okay. So now we have all this various sort of kind of flow chart, which sort of tells you. So this leaf nodes. So all the nodes that are sort of in the bottom line, they are called the leaf nodes, and this is the root nodes, and all these other nodes that we have over here are called the intermediate nodes or whatever. So now this is an example of a decision tree. So if we have like this kind of structure, then it's actually very good for classification problems. Okay. Yeah. So how we can apply this to how this philosophy is applied to this machine learning thing, let's say. Let's say we have three things. So let's say we have x1, three parameters. So these are like input variable, or not input, sort of independent variable, you can say. This is the response. Alright. So you have this. So let's say you have 100 observation. Okay. You have, let's say, R1, R2, R3, R100. Okay. And you have some corresponding values of it. Some values. Okay. So maybe let's say x1, x11, x12, x21, x22, so on, x100, 1, x102. Okay. Some values. These are all, let's take them to be real valued. It takes real numbers. And some output. So let's say 1, some is 0, some 0, and so on. Right? So this, our response variable is sort of categorical. Okay. Yes. All right. So now, sort of a new person comes in. So now, sort of a new person comes in. Let's say it's a new person. Let it be R. And the value corresponding to those parameters x1 and x2 are also given. Now based on this x1 and x2, like we want to predict whether the person has y level 1 or 0. Okay, so we're going to solve this problem and we'll see how. So I input all my data into a machine learning algorithm, and I want the machine learning algorithm to be such like it outputs me a decision tree, which is something like this. So let's say, so a person comes in, so I'm looking at x1. So if the value of the person is of x1, let's say, is some less than a, then we assign it to this class, and if it's greater than a, then we assign it to another class. So we now split the population into two classes, where you have in one population all the values of x1 less than a, and in the other population you have all the values greater than or equal to a. And then we again look at the value of x2 for this population as well as for this population. So if the value is less than b, we assign some label, say y1, and if it's greater than less than or equal to b, we assign some other label, y2. Similarly, we do it over here. If it's say greater than c, we assign some label, and if less than c, we assign some label. So we have y3 and y4. Okay. So let's say for completeness, let's say this is 1. Or let's say this is 0. This is also 0. Right, this is 1. So now we have got a variation tree based on our input data, and now we also check our accuracy and all based on the philosophy that I have kind of described initially. And now this new person comes in, and we plug those values of x1 and x2 into this decision tree. So let's say whatever the value of x1 for this new person is less than n. So the new person comes into this class, and we again check the parameter for this x2, and let's say the value is greater than b. Then the person belongs to this class with y level 1. So this is also a sort of classification way, decision tree. Okay. So I won't be like telling you like how you can come up, how the machine learning algorithm actually comes up with this kind of tree, because for that you can look at the reference that I've sent you, the Introduction to Statistical Learning by Gareth James. Okay. So now I'll sort of describe another idea which is called k-means classification, and then maybe I'll stop for this lecture. So now we'll sort of describe neighbours. So now let's say in a plane we have lot of points of two classes. One point is like this, another of this class. Okay. So we have two type of points, cross and zeros. Okay, and now let's say another. So we have two classes, right? So we have this as one class. So this is class 1, and this as class 2. Okay. Let's say now you picked up a new point. Let's say Let's say you pick a point over here. Now, so this is whatever new point. Now you want to predict whether this new point either belong to class 1 or class 2. So how would you go about it? So one possible way is to do something called k nearest neighbor thing. So I'll sort of right now tell you like a brief mathematics behind it, how you can do it. Very simple thing. So I'm rubbing this. Okay. So let's say the points in the plane was x1, y1, x2, y2. So let's say xk, yk. So we have k many points, and with each point you have some level of. So with each point you assign some level of this, or let's say whatever. So either each point belong to this cross class or zero class. Alright. So now a new point comes in. Let's say A and B. This is the new point, and you sort of want to predict or rather classify this point into either this cross class or zero class. Like how will you go about it? So for that we'll do. So we have a very simple algorithm. It's called k nearest neighbor algorithm. So what you do is you compute all the distances of this point with all the other points. So let's say your d1 is sort of the distance between this new point AB and x1, y1. Similarly, your d2 is the distance between AB and x2, y2. And going on, let's say you have dk. No, not k. I won't take k. I think k I already used over here. Let me take n. Say dn distance. For now, you can assume this distance to be Euclidean distance, but people have also looked at other distances. For simplicity, let's take Euclidean distance only, right? And after you have sort of let's say computed all the distances, then you label them in a decreasing, sorry, in a increasing manner. So let's say I have already sort of ordered them in a increasing manner. So what I have is, so without loss of generality, I can assume that I have already sort of kind of ordered them. D1 less than equal to D2, so on up to Dn. So we have this condition. Alright. Now how to use this k thing over here? So now I look at first k many points. Alright. So I look at first k many points. Right. So let's say I take for simplicity I take k to be 5. So it's better to take actually odd numbers. You'll see why. Let's say I take k equal to 5, and I look. So I look at this first d1, d2, d3, d4, and d5. And of these distances, I see which class is dominating. Let's say d1 is associated with this class, and let's say d2 is associated with 0. This is with x, this is also with x, and this is with 0. So I see this class x is sort of, because so this d1 is associated with level x because d1 is sort of your representing a value of x1, y1. So this is of class x. Similarly, d2 is of class 0 and all. So you see, of these 5 distances that we computed, we see this class is dominating. Alright. So since they are dominating, so I will say my new point, I will classify it as this class x. So let's say rather than looking at 5 points, I look at now 7 points. Okay, equal to 7. So I look at d1, d5, d6. This way. So I look at d1, and d2, and d3, d4, and d5, and d6, and d7. And I have d1 representing this class, d2 representing this class, d3 representing this class, d4 representing this class, this class, this class, this class. So you see in the first 7 points, this 0 class is dominating over x. So if I choose k to be 7, I classify my new point to be of class 0. Okay. So you see, if I take k equal to 5, I have this kind of my class is going to be this, and if I take k equal to 7, my class is going to be 0. So which class to take, like, sort of depends on your error minimization techniques, and that I can't discuss because it involves a bit of mathematics. So this way of classifying is also a way of classification. So this is called the k nearest neighbor. you can look more on this on the I think references that I've suggested to you. So yeah, this is k-nearest neighbors. So I think the technical part of this lecture sort of ends here. Yes. So I think I have described four techniques. So one was regression, and then in the classification we had logistic, then we had decision trees, and then this k-nearest neighbors. I think since I'm running out of time, I can't describe like deep learning is, because deep learning is really deep, and I think it's not a good time to give an introduction to deep learning. But I think whatever ideas that I've described to you, I think is enough to get you started on this journey with some mathematics background. So when you learn a bit of linear algebra and a bit of statistics, then you can start your journey on this voyage of machine learning. And so now, as I've told you, I'll tell you also kind of the prospect of machine learning in the current job market. See, the thing is, data are coming each day. Tons and tons of data are being produced. So we need people to analyze and build model for them. So if you are majoring in machine learning or statistics or mathematics, you can always go into these fields, data science and all. And the salary, I think each company pays in the current to current data scientists who are from like STEM background is quite, it's very high. It's almost in 7 digits. Okay. But I think it's important that you have a very good understanding of all those machine learning techniques. Like, these are very simple techniques that I've described to you. There are, I think, lots of other techniques like random forests, k-means clustering, and support vector machine and things like that. So it's very hard actually to sum all of them in one lecture. But I think I just try to give you some main ideas of what those things are, and so if you have any question related to anything, you can just ask me in the Q&A session that we might have. So I think till then, all the best.